Hello friends, welcome back to our Control System Simplified series. Today we'll discuss about the time response analysis and the standard test signals associated with this. Time response analysis is nothing but the analysis of performance of the system in the time domain. In other words, it's knowing how different system variables change their state with respect to time. This is required for us to control the speed of response, minimize the error, and a lot of other things that we learn as we go ahead in this topic. All systems have some energy storing elements like inductors, capacitors, flywheels, etc., and they cannot be avoided. When a certain input is given, the output doesn't change instantly, as these elements can't change the energy they store instantly, as they need a certain amount of time to change the amount of energy to store. The time that is required for the system to go from one state to another state is what we call the transient time, and the response of the system during this time is called the transient response. If a system is stable and well designed, the system will settle close to the desired output, and this response after the system settles down is called the steady state response. Now let's take a simple example. When we kick the ball in a setup, as we are seeing in the figure, the ball bounces a few times due to its kinetic energy and then settles. The response when the ball is still bouncing is the transient response, and once it settles, it's the steady state response. Another way to look at time response is by analyzing how the system responds to the stored energy of the system with no input given, which is called natural response of the system. Then, how the system responds to a given input, but with no energy stored initially in the system, is called actually the forced response. But we will not be considering that as a part of it. But what we will be doing is, we'll be trying to understand and analyze the response of control systems in both time domain and frequency domain in the control systems. We'll discuss frequency analysis later, but now let's limit it to the time response. Let's see what is the time response that we have seen. If the output of control system for an input varies with respect to time, then it's called time response of the control system. As we have seen, we have both transient response and steady state response. Here, both the transient and steady state responses are indicated. The responses corresponding to these states are known as transient and steady state response. Mathematically, we can call it as C of t is equal to C transient state with respect to time and steady state with respect to time. That's exactly what CTRT is, the transient response. And then if you see the transient response, after applying input to the control system, now it's like, t is equal to 0 when the switch is on, right? And then you have V of t equal to V. That's exactly happens. After applying input to the control system, output takes certain time to reach steady state. So the output will be in transient state till it goes to a steady state. Therefore, the response of the control system during this transient state is known as the transient response. So the transient response mathematically can be written as limit control t tends to 0. Let's take an example of time response C of t is equal to 10 plus 5 e power t. Here the term 5 e power minus t will be 0 as t denotes to infinity. So this is the transient time. As t to infinity, e power infinity is 0. Okay. The first term 10 remains even at t as t approaches infinity. So this is the steady state. This is the steady state and this is the transient state. So let's see some of the standard test signals. So the standard test signals are impulse, step, ramp, and parabolic. These signals are used to know the performance of the control systems using time response of the output. So unit impulse signal delta of t is defined as delta of t is equal to 0 for t is not equal to 0, and for integral 0 to plus delta t dt is equal to 1. This is exactly what this figure denotes. So the unit impulse signal exists only at t is equal to 0. Only at t is equal to 0, impulse signal exists. The area of this signal under small interval of time around t is equal to 0 is 1. The value of unit impulse signal is 0 for all other values of t, as you will see here. Then unit step signal, u of t is defined as 1 if t is greater than or equal to 0, and u of t is equal to 0, t is less than 0. That's exactly what we see it here. Okay, so t is greater than or equal to 0, your u of t input, u of t is nothing but input signal is one step, and t is less than 0, it is 0. So the unit ramp signal, you're seeing it here, and it's a steady increase. And when r of t, if it is the input signal, when r of t is equal to t, for t is equal to greater than 0, greater than or equal to 0, you will have this something t equal to t. Okay, and it is 0 when t is less than 0, it is 0. So then if you want to represent r of t in terms of unit step signal, r of t is equal to t into u of t. That's exactly how we convert it into the thing. Then a unit parabolic signal, p of t, is defined as p of t is equal to t square by 2 for all, this is a t square by 2 for all values of t greater than or equal to 0. And for less than, t is less than 0, p of t is equal to 0. This is a parabolic. So we can write unit parabolic signal p of t in terms of unit step signal t square by 2 into ut. This is how we represent parabolic signal in terms of the step signal. So the unit parabolic signal exists for all the positive values of t, including 0. For all the positive values of t, you have including 0. And its value increases non-linearly with respect to t during this interval. The value of the unit parabolic signal is 0 for all the negative values of t that we are seeing here. Okay, so that's the what we have seen about the standard test signals. Thank you very much.